Before I go into the solution for homework 1, let's go back and look at our conclusions about work. The key is down at the bottom. We can use the work-kinetic energy theorem, which is just calculating the work contributed by every force in a system, and then using that total work, or net work as we call it, and setting that equal to the change in your kinetic energy, which essentially will give us a change in a velocity. Now, one thing to note is one shortcoming of the work-kinetic energy theorem, or using energy in general, it doesn't give you information about time like motion equations do. So let's go ahead and look at the solution for homework 1. We started with the first case of a box on the floor. It's a 20 kilogram box, and you're going to lift it up 3 meters at a constant rate of speed. I just picked out a speed of 4 meters per second. And as you can see, this is constant speed, so our acceleration is 0. The first thing we'll do to solve any problem with forces is we should draw a free body diagram. Of course, I start with gravity, 200 newtons, mass times gravity. And this is a simple case because we are not accelerating. We know that this must be an equilibrium, it's dynamic equilibrium. So we have an upward force must counteract the downward force. So it's also 200 newtons. That's your lifting force. So let's go ahead and calculate the work done by the lifting force. As you can see, it's simple calculation. Remember, we have a simple work formula if the forces are aligned with each other, and these are. And we have 200 newtons times 3 meters for your lifting force, which gives you a total of 600 newton meters, or 600 joules. And that's a positive quantity because they're acting in the same direction. Gravity, on the other hand, similar calculation, but because gravity is acting downward and our displacement is upward, those are a 180 degree angle from each other, and so gravity is actually working against you lifting, and so that must be a negative quantity. And you can see in our formula, if we just use a negative 200 showing the direction of the force relative to our positive 3 meter displacement, we'll get a negative quantity here as we'd expect. Next step, let's add these up and we'll work out the total, or the net work as we call it. And the net work is 0. What does that tell us? Well, according to the work-kinetic energy theorem, the net work is equal to the change in kinetic energy, and if the net work is 0 joules, our change in kinetic energy must be 0 joules, as must our change in velocity. Of course, we knew that up front from our understanding of motion, 0 acceleration, so we don't expect to have any change in our velocity. Sure enough, that works out. Simple case. Step back and take a look at a key idea here. Work can be both positive or negative. We saw that in a previous lecture example for a horizontally moving object with a pushing force along the ground versus a frictional force working against it. Well, now you are lifting a box and you have gravity working against you. So the work done by you is positive because we are displacing it upward and the force is upward that you are applying. On the other hand, gravity is doing just the opposite. As you're lifting up, so the displacement is upward, gravity is acting downward, so it's working against you. Remember, if we want to accelerate, which we're going to do in the next problem, this force of you lifting has to be greater than the force of gravity. On the other hand, if you wanted to, as you are lifting this, maybe instead of speeding up the lift, you're going to slow it down. That means your force of lifting is going to be somewhat less than the force of gravity as you slow the box to a halt. And we'll see that in the third example. The work done on you would be negative if you are lowering the box. And why is that? If you're going to lower the box, the displacement is downward. So our displacement vector is downward, but your lifting force, you're supporting that box as it's coming down, so you are still applying an upward force. And so you are applying your upward lifting force, but we're moving downward, so we'd actually have a negative work being done by you in this case. In the same sense, if you look at gravity, now when we're moving this box downward, our displacement is downward, and our force due to gravity is also downward. So they are aligned both in the negative direction, but that's a positive work being done by gravity instead of a negative work. In the second case, we're going to take that box, rather than lifting it at a constant velocity moving upward, we're going to accelerate it. So we're going to take a 20 kilogram box, move it up 3 meters, and we're going to accelerate it 2 meters per second. And let's start it at 0 meters per second. So we are speeding up. Same idea. The first thing we want to do is we need to calculate the work done over that distance. And remember, you know how to solve all these problems using the motion equations, so you could follow that process as well, but we're going to contrast the two ideas here. So the first thing I'll do is let's draw a free body diagram. There's our object. And of course, I'd like to start with gravity acting downward 200 newtons. Because we are accelerating, our lifting force must be greater than our force due to gravity. So our upward force has to be longer than the downward force, otherwise we wouldn't be able to accelerate. We'd be in equilibrium again. So in fact, what we can do is we can do a quick little calculation using Newton's second law. We know we're given the acceleration, we know the mass, so our net force is mass times acceleration. So let's calculate ma. So ma is 40 newtons. So we know our net force acting on this is 40 newtons. And if we have positive 40 newtons, the upward force has to be 240 newtons. That would give us 240 minus 200 equals the 40 newton difference. And there it is. So that 240 newtons minus 200 newtons gets us our net force acting on it of positive 40 newtons. Quick way to do that. So now let's calculate the work that you are doing when you lift. So we're going to take the simple work equation, because these are aligned forces again. You are lifting with 240 newtons of force, and you're moving upwards 3 meters. They are aligned, matching directions, so it's going to be a positive work done by you. Positive 720 joules. In the same sense, we're going to calculate gravity, and gravity is acting opposite. This is a downward force acting opposite our displacement vector, so that's going to be a negative work done of negative 600 joules, just like it was last time. So what's changed here from the last example is your work done is actually now greater than the work done by gravity. So when we take a sum of these, we find the net work done is positive 120 joules. First, let's use motion equations, and let's figure out what the final velocity is. And I'm just plugging this right into equation 8. You can go ahead and plug in the numbers yourself, and you'll see. And I just solved equation 8 for v1. And we find out that the final speed is square root of 12 meters per second. I don't normally leave things in radical form, but I just want to see a nice clean number here rather than a decimal, so you can see where the numbers are coming from. So now let's try calculating the velocity using a different method. We're going to use energy to do it using the work-kinetic energy theorem. So as you recall, the net work done on an object, according to this theorem, is the change in your kinetic energy. And of course, the change in your kinetic energy is just your initial kinetic energy, which is on the right here, subtracted from your final kinetic energy. So it's final minus initial when we do this. Seeing as I would like to solve for my final velocity, what I'm going to do is I'm just going to do a general solution here. I'm going to solve for VF here, which I did below. I just multiplied both sides by 2, then divided the mass over to the left side, which you can see right here. I brought the negative VI squared over to the other side, which you see here, and then I took the square root to get rid of the square on the final velocity. And if you plug in your numbers, and what do you see? You get 12 meters per second again. So they match. So that just shows that we can solve for these velocities using 2 different ways now. And you'll find going forward that in many cases, if you don't care about the time that it takes to do something, that energy methods are a little bit quicker than you would find for motion equations. So the first example, we were moving at a constant velocity. The second example, we were accelerating, and now we're going to decelerate. So we're going to take that same 20 kilogram box, and let's just say we're initially moving at 4 meters per second. But then for the last 3 meters, we're going to slow down at a rate of 2 meters per second squared. So here's our box. And what we're going to do is we're going to, starting at a 4 meters per second speed, we will actually slow down as we move up 3 meters. And the rate at which we'll slow down is negative 2 meters per second squared. So once again, what we're going to do is we're going to calculate the work done over the 3 meter distance. And we'll show the contrasting calculations for the velocities. We're going to start with a free body diagram, of course. Here's our mass, gravity acting on it. And once again, we're decelerating. We don't know what this upward force will be right off the bat. It's not going to be equal because we're not in equilibrium. We're actually accelerating now. And the trick to solving this without writing out a ton of equations is just remembering that I have the acceleration, I have the mass. If I multiply the mass times acceleration, I get negative 40 newtons is the net force of this gravitational force and my lifting force. And so my lifting force has to be shorter than my gravitational force in order for me to slow down. And it has to be shorter by that much. So 160 newtons is my lifting force. Next step, we're going to calculate the work done by you lifting, and now we have 160 newtons times 3 meters. So we've reduced, in our last case we were at 720 joules, now we're down to 480 joules of the work done by you lifting. And this is you lifting and it's slowing down as you're lifting it. And let's compare that to the gravity. Gravity hasn't changed in all three cases. Gravity, we've moved up in three cases 3 meters, and in each case it's just 200 newtons of the gravitational pull times the distance you traveled. Let's find the net work done now. Just add those up, and now you have a network of negative 120 joules. So in the first case we had at a constant velocity 0 joules. In the second case where we had a positive acceleration, we had a positive network done. And in this final case we have a negative network done when we're decelerating. So let's go ahead and use our motion equations again to solve for the final velocity. And in this case, you'll see we started out at 4 meters per second, and if we plug in some numbers here, and I showed you the plugs, you actually find out that it's 2 meters per second for the final velocity. Let's contrast that with the work-kinetic energy theorem, and I'm going to use the same exact format that I did before. I took the work-kinetic energy formula, solved for VF, plugged in my numbers, and you can see this is a negative number here. And you ought to be worrying at this point, saying, I've got to take the square root of a negative number now. But we don't have an initial value of 0 anymore. We actually have a positive 4 here, and that's going to square to 16. And that'll offset that negative number. And it turns out we get the square root of 4, which is 2. And once again, they match. And so we have a second way now of calculating a velocity, a final velocity. Or you can use this to find an initial velocity given a final velocity using energy. Okay, so I asked you to complete this table. Alright, so what patterns did we find when we did these three examples? Let's take a look at the accelerating case, we'll look at first, the constant velocity next, and the decelerating case last. So first of all, the lifting work done when you were accelerating was a high number, the highest of all three, positive 720 joules. Gravity was negative 600 joules for all three of these cases. And our net work done in this case was positive 120 joules. You put more work in than gravity did, and you overcame gravity, and you sped up. We had an increase in our velocity. Of course, our kinetic energy increased. If velocity increases, our kinetic energy increases, because kinetic energy is a measure of the energy of motion. And of course, from the work-kinetic energy theory, these two quantities, the net work and the kinetic energy, should match, and they do. Similarly, for the constant velocity case, now we have no acceleration, so we have no change in velocity, and we'll see that appear in our numbers. Our lifting force is a bit lower than before because we didn't have to lift with much force to lift only at a constant velocity. Of course, that was equal and opposite of gravity, which resulted in a net work of 0. And of course, our velocity change was 0, as was our kinetic energy change. And our change in kinetic energy, once again, equals our net work done on the object, just as the work-kinetic energy theorem would tell us. Finally, let's look at the decelerating case. Well, now our lifting force was even lower than it was in the constant velocity, because we're actually going to slow down. We're going to actually lift up with a little bit less force than gravity is pulling downward to slow down. And of course, our work as a result is a little bit less in the other cases as well. Gravity didn't change in any of these cases. We're going up 3 meters, and gravity is working against us with 200 newtons. So all those numbers stayed constant for all three cases. And of course, now, because our lifting work is less than our gravity, we have a negative result for our net work. And if we have a negative result for the net work, it turns out our change in velocity is negative as well. And of course, if we have a drop in our velocity, that means our kinetic energy must drop as well. So our change in kinetic energy is negative. And once again, our change in kinetic energy matches our net work, because this is the work-kinetic energy theorem at play. So let's look at some patterns here. Summarize. When the net work done is positive, as we saw in the accelerating case, we have positive. So that means acceleration must be positive, and it turns out our velocity is positive as well, or change in our velocity. When the net work is 0, what did that mean? The net work happened to be 0 because we weren't accelerating. All right, we did not do any additional work other than directly matching gravity's force to move the object, and it turns out those two canceled each other out. And so when we have no net work, that means our acceleration is going to be 0, and our change in velocity is going to be 0 as well. Finally, when the network is negative, well, that means in this case it was negative because we were lifting with a smaller force and gravity is pulling down on us. So we had a net negative result in our work, and we were slowing down. Our acceleration was negative and our velocity, change in velocity, was negative. So when our network is negative, that just means we're slowing down. We have a negative acceleration. All right, let's step back a second and look at what we were doing with all this work we were doing, both on our part as the lifter and from gravity's part. So we did some work on the object, gravity did some work on the object, so what did it do to the box? What was the result? Well, for you, you caused the box to do two things. You changed its position, you moved it upward, and you changed its speed. That's what your work did. The question is, this is a little bit more difficult to think about, but I think it'll make sense when we discuss it. So we can see what you did when you did your work, but we know that when you do work, you should have some sort of result that you can point to after you're doing all that work. So the question is, what did the work that gravity did on the object, how did that affect the box? Well, what it did is the following. The box height increased, so now has the ability to do what if you let it go? It has a difference now thanks to gravity. You moved it from 0 meters up to 3 meters, and now gravity has something it can do to it. So the work done by gravity went into increasing the box's potential energy. So in the first case, when we, well, in any of these cases, when we lifted the box up, gravity actually did a chunk of work on it, and that gravity was stored as potential energy. So we took out this as a negative quantity, and as a positive quantity, it went into the potential energy of the object. So there's our first good example of a transaction of work is changing into energy. Now, the next part of the homework is for you to work on a similar example with an elevator. And please carefully read the scenario here. I mean, you have to make sure you're not subtracting numbers incorrectly to get floor differences. Each floor is 3 meters tall, and you have to read that carefully and figure things out. And I provide a slide for you to work out, or some space for you to work out free body diagrams for the elevator car moving up. And as a little aside, I also ask you to take a look at the elevator, somebody standing in the elevator like this elevator operator, and just ask you what the normal force he feels acting on his feet. After you draw your free body diagrams, please go through and calculate the lifting force, the work done by the lifting force, the work done by the gravity force, the net work, just like we did on the previous example in homework number 1. And then you can calculate your VI, your initial and final velocities here using the work-kinetic energy theorem. And lastly, don't forget to just make a note of what the normal force acting on the elevator operator was, just to keep in mind what happens with those forces. Finally, what I'd like you to do is to fill out this table again. Did anything change? And just fill out this table similar to what we did on the last problem. And you're going to see most of your answers are going to be the same, but we'll have different values in this table.